Hi everyone, welcome to video 2.7. We're going to be talking about precision and accuracy, and we're starting here on page 129. And yes, we are in lesson 2.7, even though I know we were just in 2.2, but this is a topic that I wanted to make sure we covered before we looped back to two-dimensional figures. Our lesson goals for this video are to determine the levels of precision and accuracy in real-world scenarios, to calculate the approximate error of measurements, and to choose the appropriate level of accuracy for measurements when we are reporting quantities. So the vocabulary word precision is the repeatability or reproducibility of a measurement. It depends only on the smallest unit of measure available on a measuring tool. Suppose you're told that this segment measures 8 centimeters. The length to the nearest centimeter of each segment shown below is still 8 centimeters. It doesn't matter if we are before it in this blue line, after it in this green line, or pretty close to it, but still after it on that line that's red. And our second vocabulary word of accuracy is the nearness of a measurement to the true value of the measure. And so if we consider these target practice results shown, the targets demonstrate the various levels of precision and accuracy. So precision, repeatability, and accuracy, nearness to the actual true value. So this first example is the only one where we would say it's both accurate and precise. Means that the 5 different shots are in the same area and that area is close to the target. Here we have accurate, close to the target, but not precise. They're kind of all over the map. Then over here we have in the third example, precise, but not accurate, not in the bullseye. And then this last example is neither accurate nor precise. So in example 1, we have an example of horseshoes. Says Ali and Isha are playing horseshoes. In this game, each player has 2 horseshoes that are thrown as close as possible to the stake in the middle of the pit. And we have results for 4 of the innings that are shown on page 130. The question asks us to label each horseshoe pit in all of the 4 different ways that we saw on the previous page. So accurate but not precise, precise but not accurate, both accurate and precise, or not accurate or precise at all. Let's see what our examples look like. So our top left example, we see all of the horseshoes are right around the stake and all 4 of them are there. So we are both accurate and precise in this case. In our top right case, we can see that they're all pretty much in the same area, but it's not the area they needed to be in. So they are precise because they're all kind of in the same area, but not accurate. It's not where they need to be, where the true scoring is. Bottom left example, we can see that we're very close to the stake, but not precise in all kinds of different directions away from the stake. So accurate, close, but also around that middle instead of close to it. And then we have on our last example, neither, I hope you can see, neither near the target or the stake, so not accurate. And definitely none of them are near each other, so nor precise. So we have a new check on page 130 on this same idea of precision and accuracy. This time we have lawn games. So Kate is playing beanbag toss, or of course we know this as cornhole, with her friends. Teams of 2 take turns tossing beanbags at a raised platform with a hole at the far end. And when a team throws or knocks their own bag into the hole, they receive 3 points. So we're looking at the end result boards and asking to label them in the same four combination ways that we have. And we only have two choices here, so you'll have to choose what makes sense among the four choices that are given at the end there. So take a pause in the video and see if you can apply the correct vocabulary word to each scenario. All right, our next concept is called approximate error. So in the world, measurements are always approximate. And in the approximate error of a measurement can help you determine how accurate your calculations are going to be using that measurement. So we have a key concept here on page 131, and it says the positive difference between an actual measurement and an approximate or estimated measurement is its approximate error. So E sub A. And that's always going to be the actual minus the estimate. But notice it's the positive difference. So this is why we have those absolute value there. So in example two, we're trying to find the approximate error. It says a student weighs a 10-gram precision mass on three different scales, and we're to find the approximate error for each of these measurements. So in part A, we have a spring scale that weighs it at 9.86 grams. We have a lab scale that weighs it at 9.92 grams, and C, a food scale that weighs it at 10.3 grams. So the approximate error, remember, is going to be the difference for each one of these from the 10-gram precision mass, and then made that difference positive, absolute value. So for A, our first example, you can see they've already set up the subtraction for you, 10 minus 9.86. So the actual measurement minus the estimated measurement, or 0.14 grams. In part B, we're asked to fill in that second blank. And so we have the actual measurement of 10 minus the estimated measurement. So that's the 9.92 from the lab scale. And that difference, absolute value, is 0.08 grams. In part C, we have our food scale measurement estimate. And so that difference with an absolute value is 0.3. Pretty simple, I hope. In our check for example two, we're asked to find the approximate error. We're told the temperature in Portland, Oregon is 35 degrees Fahrenheit. Declan measures the temperature outside his house and the thermometer measures 34.2 degrees Fahrenheit. What is the approximate error of the temperature? Take a pause on this video and see if you can figure this out. All right, lastly, we're going to talk about calculating with rounded measurements. So when you are rounding to a place value, you always want to look at the value immediately to the right of the position. If the value is 5 or greater, then you round up. So for instance, 42.64 rounds to 42.6 because 4, this digit here, is less than 5. We're not going to take this 6 and round to the next tenth up of 7. 42.57 also rounds to 42.6 because this 7 digit to the right of the 5 is greater than or equal to 5. So we're going to round to the next tenth above the 0.5, which is still zero point 0.6. So if we're given a measurement of 42.6 centimeters rounded to the nearest tenth, the actual measurement could be any value in a range of values that will round to 42.6. And we can see that there's a range of numbers for sure that that would apply to. So let's look at an example to see how calculating with rounded measurements can make the outcome different. We have a carpeting example, and Alejandro here is wanting to carpet his bedroom. He's measuring the dimensions of his bedroom and rounds to the nearest foot. The carpet he chose cost $2.63 per square foot. So in part A, it says, what is the possible range for how much it will cost to carpet Alejandro's bedroom? And then in part B, it says Alejandro checks the dimensions of the room and measures it to be actually 9.8 feet by 8.2 feet to the nearest tenth. So how does changing things to the nearest tenth change the range for the cost of the carpeting? All right, so part A is going to be rounded to the nearest foot. Part B is rounded to the nearest tenth. So to start off in part A, we want to find a possible range for the area of the room. So first of all, one dimension at a time. Our 10-foot measurement of actual length here could actually be 9.5 could be less than or equal to that length. In other words, that length is greater than or equal to 9.5 or less than 10.5. In this range right here, we would still round on this end up to 10 and on this end down to 10. Then the other dimension of 8 feet being the actual width, same idea. In this range, we would round up to 8, and in this range, we would round back down to 8. So if we wanted to calculate the least possible area, we would take these two smaller measurements and we would multiply them. And with our calculators, we can see that's 71.25 square feet. Notice the units there, square. Then the greatest possible area would be taking those larger measurements and multiplying them, or getting 89.25 square feet. So the area is going to be at least this much, lower end, right? Less than or equal to at least 71.25 square feet, but less than 89.25 square feet. Now that we have that range, we want to calculate the cost. So in step 2, we want to take that least possible area of 71.25 and multiply it by the cost per square foot. And you see that we have already in there $187.39. And hopefully you are seeing that we want to round to the nearest penny, of course, since we're talking dollars and cents. So we want to do the same for the outcome on the greatest possible area. And to do that, we're taking our 89.25 and multiplying it by the cost per square foot. So make sure you're putting that into your notes. And then on your calculators, you can see that we are again rounding to the nearest penny. We get $234.73. So the cost is going to be at least that lower number, 187.39, but less than 234.73. So let's see what happens if we change the precision level of our original measurement of our room to the nearest tenth. So this time we're going to start with a different range for the measurements of the room. So again, we still want to talk about rounding, but this time it's 9.8 feet for our length and 8.2 for our width. We're looking for numbers that on the lower end will round up to 9.8 and on the upper end will round down to 9.8. So hopefully you can see, remember that digit of 5 or more. So 9.75 or more would round up to 9.8, and that digit of 5, not 5, but 4 or less actually, would round down to 9.8. And then again, the same idea of that range of values for the 8.2 measurement. And so we'll go ahead and multiply those smallest measurements, 9.75 times 8.15, fill that in, and then we get 79.4625 square feet, where the greatest possible area is going to be multiplying those two upper measures, 9.85, fill that in, times 8.25, and our calculator gives us 81.2625 square feet. Let's see what that does to the cost. If we take our cost for the least possible area, which will be the lower number, 79.4625, times $2.63, of course, per square foot. That has not changed. The tenths level of precision gives us a least possible cost of $208.99. And then the greatest possible area takes our larger number for the area measurement times that cost per square foot. And here we get $213.72. So the cost is going to be at least $208.99, but less than $213.72. And so we can see how much of a difference happens with the change in the precision level of the measurement. And here at the bottom of page 132, it's stating just that when the measurements were rounded to the nearest whole foot, the range of cost was more than $45. But if we changed our level of precision to the nearest tenth, the range of cost is only $4.75. So the more precise we can be with our measurement, if we're the contractor for this job, we would want to make sure that would allow us to budget better for the job. So there's no check on this type of example here, but do be aware that your practice will have you walk through some of these calculations with rounded measurements at different precision levels. Okay, everyone, this is the part of the video where you really want to check back on the answers to those checks that were assigned to you as you were watching. All right, the correct label for the first cornhole game outcome that you see there is this is both accurate, close to the hole, and precise. The second example is that it's mildly close to the hole, so somewhat accurate, but kind of all over the map, not precise. For the check on page 131 of example 2 concept here, we're asked to find the approximate error of the measurement. So that's just going to be a quick absolute value and a subtraction. We're going to take the actual measurement of 35 degrees, and we're going to subtract the estimated measurement of the thermometer, and we will get, of course, 0.8 degrees Fahrenheit. And like we said, there's no check for example 3, so that takes us to the end of our video notes, and we'll see you in the practice.